So in this lecture, we will start the polarization of the wave. So what do you mean by the polarization? Wave polarization is the electric field orientation as a function of time at a fixed point in space. For example, if the wave is propagating in particular direction and we see at particular point, for example, wave is traveling in this direction and we want to see at this point. So what is the orientation of electric field as a function of time as the function passes? So what is the direction of electric field varies, how it changes, how it orients? That is the polarization of the wave. That is, it may be regarded as a locus of the tip of electric field intensity in a plane perpendicular to the direction of propagation. This a plane which is perpendicular to this direction. In this plane, what is the locus of the tip of the electric field? Okay, so at a given point as a function of time. So the wave polarization will give the figure that the electric field traces out while propagation. So when it changes, electric field changes with time and in this plane. So some sort of figure may be made by this tip of the electric field. So based on these three figures, we have categorized the polarization into three types. One is called a linear or plane. That is, the tip of the electric field describes a straight line with time. So if electric field is varying in a straight line, for example here or in this direction, then it is called a linear polarized wave. Similarly, we can have a circular. If the tip made the figure of circle, then it is called the circular polarized. That is, the tip of the electric field describes a circle with the time. Similarly, we have the elliptical. The tip of the E describes an ellipse with time. So here, if we fix some location, for example, let z equals to 0, these are x and y, and wave is propagating in the z direction. So at this point, so if we let take some z equals to 0, some value, so if the electric field vector is in this is the electric field at particular time, and as the time passes, it only remains the same direction in the straight line. The magnitude changes at time. This direction may be either in this way or in this way. Then it will become a linear. Similarly, the direction and the this in this case the direction is only changes and the magnitude is same. For example, it is as the time passes it changes in this fashion. The direction is changing while the magnitude is same, so it will make the ellipse. In this case, if the direction as well as the magnitude is changing with time, then it will make the elliptical form of polarization. So you can view in this have animation. So this one is a linear as we focus on the time. So it is uh, at a particular point in the space, it is varying in this fashion, linear fashion, as the time passes. Similarly, it is making the circular, and here you have the elliptic figure. So this is the linear polarized wave, and this is the circular, and this is the elliptic polarized wave. I have already shown you the animation of EM waves, so we can also see that one in the previous lectures. For example, electric this wave is propagating in the x direction. Then let this is the electric field varying in the space and moving in this direction. Similarly, we have the H fields. So now the we fix some point here at this point. So this is the electric field which is varying with time at the same point. So somehow the direction is almost in the straight line, this line. This is a vertical direction. And here the magnitude is changing. So this type of wave which is moving in this direction is called the linearly polarized wave. Okay. So we'll see it. So here we have all those three. Now we will analyze one by one all those three type of polarized waves. So let me start with the mathematical analysis. Let the wave is traveling in the z direction. Then the electric field component in x and y direction are given by these two ones. So previously we have taken E in the one direction. Now E can be in the any direction, but it will be perpendicular to the z direction, z axis. So let's take the general case where we have two components. If it is a z axis, so electric field, this is a plane. So electric field may be in any direction in this plane. So if you take any general direction, for example, if you take this direction, so it will have two components. If this is z, so it will be either x and y. So you will be having x and y component. So we take both one. Let we have the x component is given by Ex of the electric field, some constant Eox, and cos omega t minus beta z. So this is a component which is moving in the z direction, and it is along the x-axis. Similarly, we have the Ey, which is also moving in the z direction, but it is some sort of leading the x component by delta amount. It can be any general case. So let's take this delta amount, which is a phase shifted one of the. So Ey is out of phase with the Ex by amount delta. So here in this case, it is Ey leads the Ex. So we have two components. Now based on these, this value delta and the EOX, we will have the three type of the polarized wave. So EOX is the amplitude of wave in x direction, EOY the amplitude of the wave in the y direction, delta is the phase angle by which EY leads EX. So delta is here is the phase angle. So the instantaneous total electric field is given by total field will be the sum of these two components, which is E equals to EX plus EY. So we can sum them. E equals to EOX cos omega t minus beta z AX, and here we have this one. Now here if we show these two component of the electric field in this xy plane, so here we have page is the xy plane and z will be perpendicular to this xy. So you can find that the z direction will be outward from this page. So Ex is this component, Ey this one. So if you add this, E is the vector. This is the final resultant of these two, and so the electric field will be orienting in this direction. So now this is the magnitude of this electric field, and here it is the phase phi with respect to Ex. So we have Ex equals to Ux this one, Ey this one. So when you put here, we have put the z equals to 0 because we want to figure out the polarization at particular point in the space. So we have to fix the space here. So let at z equals to 0, the equations will become Ex equals to function of omega t and Ey is a function of omega t at this point, the origin z equals to 0. So the magnitude of E is given by this one, sum of these magnitude of these two, and the phase of E, this angle phi, is given by the Ey over Ex, magnitude of these 10 inverse of magnitude of this ratio of these two. So phi equals to 10 inverse Ey of Ex, and we put Ex from here. So what is Ex? Ex this one. So you can put EOY cos omega t plus delta, EOX is the cos omega t. So here is the magnitude. This is the direction AX and AY, and this part is the magnitude of this vector. Here we have the magnitude of this vector, this one, and these two direction. So putting here magnitude, you will getting the phi. So what we can see, this magnitude of E is a function of EOX, EOY as the time, also time and delta, the function of time, delta, and EOX. Now we can say E with the time varies, this magnitude may vary in general. So if the time varies, if a time passes, this magnitude is a function of time, so it may vary with time, it may decrease or increase. Similarly, we can see the phi. Phi is also a function of time. So now if you fix the delta, there is and fix EOY, EOX as the time passes, this phi may also vary with time. It may be decreasing or increasing depending upon the time. So here it means this in general, this magnitude and this phase may vary with time. So as the time passes, this may orient in this way, this may be orienting in this way, this may be going in this way, so and so on. So this electric field may vary with time in the particular point in the space. So the tip will make some sort of figure. So it may make the linear figure, or it may make the circular, or it may make the elliptic. Now we take the one by one. So magnitude and phase of each change with time depend on time. So for the linear polarization, what we have, if delta is equals to 0, that is both components are in phase. So if the both components are in phase, what will happen? Ex becomes EOX cos omega t, and EOY is the cos omega. They have the same phase. So when you take the magnitude, you will have the EOX square plus EOY square, and this is here. So still the magnitude is a function of time. As the time passes, this function, this magnitude may change with time. However, when you see the phase here, so when you put up tan inverse EOY cos, it will cancel out. Now it is independent to time. Once you know the electric field, these values are fixed. So tan inverse EOY EOX will be fixed. So now this phi will be fixed. This phi will be fixed, and now that this is a function of time. So the time passes. Now this phi will remain same. So either the magnitude may change. So it may be in this direction, or it may be in this direction, but this angle will remain same with this one. The magnitude may be reverse, may decrease, increase, but the phi. So it is called a linear polarized wave. So the phi is independent to time and is constant. As phi is constant, the wave is linearly polarized. So you have the linear polarized wave. So the condition for linearly polarized wave is that this delta should be 0. That is, the both x component and the y component should be in the same phase with respect to this wave. So they will have a no leading or lagging between these two. So they are in the same phase. The waves are in the same waves, both component, and they will make you the linear polarized wave. Though the EOX and EOY is different. Now if Ux equals to 0, so if Ex component is absent, then phi is becomes 90 degree. So Ux is equals to 0, then it will become infinite, and then phi equals to 90 degree, and the wave is vertically polarized. So Ux is 0 means that if you see in here, so this is 0, so resultant will be in this direction. So as the time passes, this only changes in this fashion. It will be the linearly polarized, but now it is if the y-axis in the vertical direction, so it will be called the vertically polarized wave. So if somehow Ey is 0, then the resultant of this vector will be here, and now it is called a horizontally polarized wave. So we can have the vertically polarized wave, or we can have the horizontally polarized wave depending upon the value of EOX and EOY. Now second type of polarization is the circular. So in this case, let take EOX equals to EOY. So we equate the magnitude of the each component to E naught, and delta, let take, is plus minus 90 degree. So the waves are out of phase. The both component are out of phase by 90 degree, maybe lagging or leading. So it may plus, if it is plus, it is leading EXY. If it is minus, it is lagging the EXY. Now if we take the magnitude, so because these two magnitudes are same, so we can take it out here, and this will become the cos square omega t plus sin square omega t, and you have the E naught. So now magnitude is independent to time. So it may remain fixed. As the time passes, the magnitude remains same. And this is also, you can say that if E square Ex square plus Ey square is equal to E naught, it will be a equation of circle also. That x square plus y square is some constant a square, so it will become a equation of circles. So now what about the phase? So if we found out the phase equals to tan inverse EOY cos omega t plus minus 90, because you have EY is given by this factor put up here, and EOX is given by cos omega t. So when you have tan inverse, so when you change cos omega t plus minus 90, so it will be tan inverse minus plus sine omega t. You change this sign, and you have the cos omega t. These two are equals, so they will be cancelled out. So this will be minus plus tan inverse. You can take it out this sign from here. Tan inverse, it will be tan inverse tan omega t, and you have phi is equals to minus plus. So minus is for when delta is positive, and plus sign when delta is negative. It is the inverse of this sign. So if delta is positive, this will comes out to be negative. If delta is negative, then it comes out to be positive. Signs will be reversed here. So what means that now this angle phase angle phi is a function of time. It is a linear function of time, and as the time passes, this value changes with time linearly. So now the phase is a function of time, and the magnitude is constant. So what will happen? This will make a circle. So you have this one, and you have now this is changing with time. Phi is changing with time, and this phi is a function of omega t, and this is constant. So either it will change in this direction, phi is decreasing, or phi is increasing. So as if it is minus, as the time passes, it will become a smaller, and it will go in the negative direction. If it is positive, it will go in this direction. So it can rotate either in the clockwise or in the anti-clockwise. But the distance, this magnitude remain constant, so it will make a circle. So it will make a circle. So either it will be moving in the clockwise direction depending upon the value of this positive or negative, or anti-clockwise direction. We have two types of circularly polarized wave. So the magnitude is constant and the phase is varying with constant rate, thus the electric field vector traces the circular path. So if delta equals to 90, phi is equals to minus omega t. So now this will move, this vector will move in this fashion as the phi as the t passes. So now this is phi will change such a fashion, this it will rotate this vector in this direction. Okay. If delta equals to minus 90 degree, then phi becomes omega t, and now then it will rotate the vector in this anti-clockwise direction. So this case is called the left circularly polarized wave. Why? Because if we put up the left hand of our thumb of our left hand in the direction of the z-axis where it is propagating. So in this case, we assume that the wave is propagating in the z direction. We have taken here the function of z, omega t minus z. And z, if we put up your left hand, the thumb of left hand, the direction of the z, the finger will give the direction of rotation. So in this case, for if you put up the thumb in the z direction, which is outward from here, now the left fingers of left hand side will match the direction of this one. So this is called the left circularly polarized. As the direction rotates in the left hand screw with respect to direction propagation, and this is also called the anti-clockwise. So why it is called the anti-clockwise? Uh, because if you see from the back side, this is a wave is moving in the z direction. So if z is this one, and you're moving in this direction, z axis. So instead of seeing from this side, we are watching this from, for example, this is a plane where we are watching the figure of polarization wave. So if you are watching from this side, the direction of moving this circle will give you the whether it is anti-clockwise, clockwise. So in this case, because you have the wave is moving this direction, and it is making here in this fashion is rotating. When you see from here, so it will looking as a moving in the anti-clockwise direction. That's why they are naming it to anti-clockwise. So this is easier to remember, left circularly polarized or right. So you see that the movement of this circle, rotation of this circle is either according to the right hand fingers or the left hand fingers by pointing the thumb of your hand to the direction of the propagation of the axis. Okay, so for similarly, if you delta minus 90 degree, then phi equals to omega t, and it is called the right or clockwise circularly polarized wave. So circularly polarized wave is a sum of two linearly polarized wave with 90 degree out of phase and equal magnitudes. As we have seen here, the two waves are the linearly polarized EX and EY, and then you can add up those two to get circular. So you can see the animation here also. For example, here we see a wave is moving in the Z direction. So what do you see here? It is left circularly polarized. If you take the direction of thumb in the direction of Z, then this resultant is moving, rotating in this direction. So you can see as the wave is coming, this is a two component. This is we have what will happen. So here we have two components. This is let EX and this is EY. So we have EX here, which is in this along this axis, and EY along this axis. So let this Z direction. So we have sum of these two is this vector. Now you are focusing at this point, so it is moving in the circular fashion. For the linearly, I have already shown earlier, so you can see it again here. So we have if we have the single wave, we have electric field, only one is present, Ex is 0. So this direction of electric field give you the type of polarization, and here it is the linearly polarized wave. You can see it again once more. So here how it is moving. And you have also this is another animation. So here also it is a left circularly polarized wave. Okay, because we have to see the direction of propagation. We have to made our thumb the direction of propagation, see whether it is left hand sense or the right hand sense. Then you can identify whether it is the left circularly polarized or the right circularly polarized wave. So this is the left. You can also see the right one. So here it is the right circularly polarized wave is moving this direction of this axis. So now next is the elliptic polarization, which is a very general case. So here again both are different and there is some delta. So when you can rearrange these equations, you write so cos omega t is ex over eox, and you can open this with this formula and replace cos omega t by ex over ex. Then you can find this is the equation of ellipse. That is the axis we are generally x over some constant a. You have xy, that is a and let b. This is y over b is equal to some constant. So here you have the equation of ellipse. So this is generally equation of ellipse, and when you have delta is equal to plus minus 90, so this will not become a circle until ex and this eox and eoy is not equals constant. Both should be same to make the circle. So here if they are different, so still it will be an ellipse, but the axis of the ellipse are parallel to the coordinate. So we have the major and minor axis which will be parallel to the coordinate x and y coordinates. So it is a general ellipse and it is a specific ellipse where the major and minor axis of the ellipse align to the coordinate of the space. So now if delta is plus minus 90 and EOX, EOY equals to E naught. So if we both become equal, then this will be taken out from here. It will be just EX square plus EY square equals to E naught and will be the equation of circle. So it will become a circle. So in general, what will happen? This will be, if this is a function of time, this is also a function of time. So when it rotates, so it will make a different distance here. Here it will be different. Here it may go here. It may go here. So phi is also changing with time, and this is also changing with time. So it will make a ellipse. And in general, it is the equation of ellipse. So it will make a ellipse. So we can say that we have here a ellipse. You can say this figure is sort of ellipse. So because these magnitude are not constant, so this magnitude is a function is changing with time also. So this is a elliptical polarized wave. So I stop it here and continue on the next topic, the next turn.